In the last couple of videos, we set up some properties of limits that we were talking about, where we set up some kind of formal rules about what we can do whenever we're taking the limit of different functions. And we set up 6 different rules here. And the last video, we did a couple examples where we were able to sort of separate really simple functions. Like in this first example, we separated the function x plus 1 that function into these two separate terms. And we were able to take the limit of the x term and the limit of this 1 term separately. And then we did sort of a similar thing for the next example, where we said we were multiplying some function by a constant. We found out that we were able to pull that constant out of the limit. And we were kind of able to almost create a new property of limits. And this is going to be a property that's going to be very helpful for us to sort of remember in the future, that we're able to pull a constant out in front of a limit term. And now what I want to do in this video is I want to do another example, kind of continuing on just giving examples that sort of demonstrate these limit properties. So now we're going to take a look, call this example 3. Let's take a look at the function. If we were going to take the limit as x approaches, let's say x approaches 2 of the function, let's say x to the 4th plus 2x squared minus 5x plus 7. So let's say that was our complete function that we were dealing with. And so now the first step that you can probably think of, and this is, it's a more complicated function. You probably haven't gone over how to graph something like this, so you might not have a great idea in your mind of what this function looks like if we were to graph it. So probably the best thing to do with a function like this is to actually just go ahead and break this function down into a whole bunch of different limits that we can come up with, and then we can sort of evaluate each limit on its own. So we know that this limit operator, we can distribute it sort of past these plus and minus signs, right? So we can rewrite this. So we can, let me get a bit better color. We can rewrite this as the limit as x approaches 2 of this x to the 4th term, x to the 4th, plus the limit as x approaches 2 of 2x squared, except I'm going to go right ahead and I'm going to pull this constant out in front of my limit. And from the last video, we know that we can do that, right? We can say that I've got some function f of x, which is just going to be 2, and then some other function x squared, which is my g of x, and I can just rewrite these, and I can pull this 2 out in front of the limit. So I'll change colors even, and write that as 2 times the limit as x approaches 2 of the function x squared. And so now I'm going to just do the same exact thing with this next term. We can even rewrite this as minus 5 times the limit as x approaches 2 of just that x term. And now we know, and even I'm going to skip a step here with this last term, and we know that if we were to take, and we're going to sort of distribute this limit operator, and we're going to be taking the limit as x approaches 2 of just this constant term, of just this 7, right? So we know that the limit as x approaches anything of just that constant is going to be equal to that constant, right? So I'm just going to go ahead and I'm just going to bring that 7 down. Now, I'm not going to rewrite it as the limit, because we know that that limit is just going to be equal to 7. Okay, so now we've simplified this function quite a bit. We've simplified it into the limit as x goes to 2 of x to the 4th plus 2 times the limit as x goes to 2 of x squared minus 5 times the limit as x goes to 2 of just the term x. And even let's just simplify this term really quick. And this is a pretty obvious simplification. We know that the limit as x approaches anything of just the function x it's just going to be equal to that anything, right? It was equal to anything that that x term was approaching. So this is going to be minus 5 times 2, right? And so now, even if we just brought down, that was, so minus 5 times 2, that's equal to minus 10. And if we brought that down, minus 10 plus 7, we can simplify all of this stuff. So all of this stuff at the end of our function. Maybe I'll write it there. I'll write it like that so it looks, so we can see that we're explicitly subtracting this stuff off. This is going to be the same thing as minus 10 plus 7. So that's just going to be equal to minus 3. So now we've simplified this function a lot. We've simplified it down to the limit as x goes to 2 of x to the 4th plus 2 times the limit as x approaches 2 of x squared, and then both of those terms minus 3. So now let's go ahead and let's go back to our limit properties and see which rule can we use to help us evaluate these a bit more. And you can probably see I'm going to use this product rule that we're looking at right now, where if we took the limit as x approaches some value of g of x raised to some power, that's going to be the same thing as if we moved that limit inside of the power, because the power isn't a function of x. The power isn't changing with x, so we can just move that limit inside the power. So let's just go ahead and do that. So this, I'm all the way over at the edge of my electronic paper. So this is going to be equal to, the limit as x approaches 2 of just x, and all of that is going to be raised to the 4th power. And then we're going to add on plus 2 times, put that in brackets, the limit as x approaches 2 of x, and then all of that squared, all of that raised to the 2nd power, and then we're just going to bring down that minus 3 again. And so now this is starting to look really easy and really familiar, and we've just got pretty much that second property of limits, once again, staring us right in the face, and staring us right in the face 2 times over, I guess. So we've got the limit as x goes to 2 of x, and also the limit as x goes to 2 of x. We've got that twice. So this is going to be equal to, we know both of these are just equal to 2. That's equal to 2. And then, if we brought down the brackets, that would be, we are just going to be raising that to the 4th power. Then add that on, plus 2 times 2 squared. And then bring down our minus 3 again. Put my equal signs right there. And so now we've got all of the numbers, and we can just sort of plug and chug and figure this out. So 2 raised to the 4th power, that is 16, plus 2 squared, that's 4, times 2, that's 8, minus 3, that's going to be equal to 24 minus 3. So therefore, this is all going to be equal to 21. So that is going to be the answer to this limit problem. So it was sort of a hairy problem that we started out with. Now, one of the things I want you to realize about this limit problem is that pretty much what we were doing to simplify this limit problem was this was just a polynomial, right? We've gotten, hopefully you've heard that term polynomial before. Polynomial is just, we've got x's raised to positive powers, and we've got coefficients before them. So maybe I'll do another video on this in a second. But really, all that we're doing, this value that we got at the end, and maybe, actually, you know what, I think I'm going to do another video on this just in a second to kind of solidify this concept, because it is sort of important. And it's especially important to do all of the easy problems in your calculus textbook on limits, and we don't want you to miss the easy problems that come at the beginning of the course. But this is pretty much what we were doing. There was no reason, and you can sort of think about it, if if we were to graph this, or if you were to plug this equation into a grapher, this is going to be continuous, right? There's no reason you can't plug any number you want into this function and get an answer out of it. And every single point along that line, or along that curve, or along that function, is going to be approached to by the previous point and approached to by the point directly after it. So this is going to be a continuous function that we've got. So really what we're going to find is that this is going to be equal to, if we called this f of x, that is going to be equal to if we just plugged 2 into everywhere we have an x term here. So that is going to be equal to 2 to the 4th plus 2x squared minus 5, or I don't mean 2x squared, I meant 2 times 2 squared times 5 minus 5 times 2 plus 7 at the end there. So we found out that if we were to take this limit of this long polynomial, that was going to be equal to the same thing as if we were to just take this 2, take this term, this constant that x was approaching, and we were to just plug it into our function. And so now we have got a pretty powerful, sort of, you can almost say, a new rule that we're going to use to evaluate these limit problems. And that is, if we have, let me write it down here. If we have the limit as x approaches some value a of a function f of x, and f of x is a polynomial. And so if you've never heard the term polynomial, that means that f of x is going to be equal to some a, or let's say a plus bx plus cx squared plus dx cubed, and I'm going to keep on going, for however long this pattern goes for, and then we're going to finally get plus whatever number, we'll call it just z x, let's say x to the n, whatever power of x we have at the end. Or else, actually, I think the way this is normally written, actually, you know what? Maybe I'll you know what? I should do this. I'll write the definition of polynomial a bit more like it's always written. We'll say that this is a1 plus a2x plus a3x squared plus a4x cubed, and then we're going to keep on going plus, and then our final term is just going to be an times x to the n minus 1. However long we keep going, we've just got this this function that's a polynomial. We've just got coefficients in front of powers of x. And what we found out in this video is that if we have this situation where f of x is a polynomial and we're taking the limit as x approaches some value of this function f of x, that's going to be equal to, let's say, limit as x approaches a of our function f of x, and we know that f of x is a polynomial, that f of x is in this form where we have coefficients that are constant coefficients times powers of x, positive powers of x too. Remember, all of these powers that we have on x, these are all positive. That this is just going to be equal to the same thing as if we just plugged this number a directly into our function. So anyway, this is a pretty powerful rule, and it's really going to be the central rule to evaluating most of the easy limit examples that you're going to see at the beginning of your calculus course. So anyway, with that, I'm going to end this video here, and the next video we're going to start doing some more limit examples. So thanks for watching, and I'll see you soon.